Welcome back for the next session. And before we start, I just have one announcement for the student participants. Please submit the feedback to me. I have the envelopes and you can just submit them to me. And so we start this session. Amit Ghoshal would chair this session.
Hi, good morning and thanks for being back here in time. So the first talk this session will be by Kedar Damle on impurity-induced moments in frustrated magnets.
Okay. So I'm going to tell you a little bit about the interesting physics that comes up when impurities are doped into frustrated magnets. And most of the recent work, I'll talk about the actual numerical work, the detailed calculations, is all due to George Wren, who's just about finished his PhD at the Max Planck in Dresden, and Sambuta Sanyal, who's now a postdoc here at ICTS. And the work of George relies quite heavily on some earlier work that Arnab Sen had done at TIFR for his thesis. So I'll also have an occasion to review some of that as background for the work of George. So let me begin with a small introduction, since it's a short talk. We know many examples dating back 30, 40, 50 years, where if you dope impurities into insulators, you get interesting spin physics. Perhaps the best studied old example of this is phosphorus doped silicon, where every phosphorus you can think of in the insulating silicon matrix as a kind of a hydrogen atom with a positive core and an electron that's rather loosely bound to it with the effective core radius. And in the dilute limit, these are far away from each other when the density of dopants is small, and you basically have a sort of a half-filled Hubbard model on a random lattice, and it's an electrical insulator. And the low energy physics is all the physics of the spin half moments associated with each of these unpaired electrons. And that low energy physics has a very nice pictorial description that was popularized or developed by Bhatt and Lee. The idea is that you have a spin exchange Hamiltonian with a very broad range of exchange constants because there's a range of distances between nearest neighbors. And the susceptibility can then be thought of as being made up basically of two pieces. One piece coming from sort of inert pairs that have binding energies that are quite a bit bigger than the temperature you're at, and these don't contribute. And pairs with binding energies or singlet triplet gaps much smaller than temperature will contribute a Curie sort of tail to the susceptibility. So the susceptibility behaves like some density of these active spins, which are the number of pairs that can be broken by thermal fluctuations divided by temperature, that's the Curie tail. And these in practice, in the detailed calculation of Bhatt and Lee, behave like some sort of non-universal power law singularity with the power set by the concentration of phosphorus. And in fact, the power varies slowly with the range over which you fit it, the range of temperature over which you fit it. So this is sort of known as the Bhatt-Lee phase or the Bhatt-Lee phenomenology of random singlet physics. And this motivated a huge body of work in the 80s and 90s on strong disorder renormalization proof approaches to problems like this, where there are broad distributions of exchange couplings. In one dimension, it was possible to make this picture of Bhatt and Lee asymptotically exact in the low temperature limit in a very precise way, beautiful work of Daniel Fisher that built on earlier work of Dasgupta and Ma. And the result in one dimension was that the susceptibility is basically as close to Curie as you can get, and the correction is only logarithmic. This factor is just the log of the temperatures. So it's log square heat. And for higher dimensional problems like the original Bhatt-Lee system of phosphorus doped silicon, the situation has remained largely sort of unclear in the sense of exact solutions or precise statements that are asymptotically exact. Their phenomenology clearly works and explains experiment, but the question is, in the low temperature limit, what's the sort of asymptotic limit of the density of states? And that's remained unresolved because the strong disorder RG procedure becomes inconclusive in higher dimensions. The other example we know for many years now is non-magnetic impurities. So that was a magnetic impurity in an insulating non-magnetic matrix. Now you also have examples where you put a non-magnetic impurity in an insulating antiferromagnet. The best example of this is, for example, zinc substitution at the copper site in cuprate antiferromagnetic insulators, where there's very beautiful work of many people reviewed very nicely in this review, for example, where it's known that when you do this, although zinc is non-magnetic, it induces a characteristic spin texture around the dopant position. These are static dopants. And this characteristic spin texture is picked up by local probes like NMR. What NMR really does is the position of the line, the night shift, it's measuring the local spin polarization of the spin system. And so in effect, it averages over this texture and you get a histogram of the values allowed in a texture. You get a shape of the texture by measuring. And the general idea in all these things is that the impurities disturb the system locally in some manner, and the background or the host system, the original ground state, reacts in some characteristic way. And if you can do some local measurements, you can pick up these characteristic responses, and they are a diagnostic of the underlying ground state in the absence of impurities. That's sort of the idea. That's why this is a very attractive probe of things like quantum spin liquids, where there's no order parameter, and there's no direct experimental sort of smoking gun signature where you just say there's an extra Bragg peak you've seen, so it's this state. So let me give you some background in a couple of classical examples now. So some years ago, we looked at the effect of gallium defects in SCGO. SCGO is this rather complicated spin liquid material where it's the chromium that is the spin, and that's the black dots here. And in this short talk, I don't really want to take you through all the details of the physics of this material. Let's just focus on the fact that the chromiums basically form a Kagome bilayer, which is very well separated from the next Kagome bilayer by a layer of inert spin dimers that you can just think of as lots of independent pairs of spins that really do nothing, at least in the pure case. And the other thing to remember is that the idealized formula that people write down is never actually realizable. And the best samples always have at least 5% of excess gallium. And gallium being non-magnetic, it actually substitutes for the chromium sites, and it can be thought of as a non-magnetic or a non-magnetic impurity or a vacancy in the magnetic lattice. And there's some slight bias for these gallium to go and break up these spin dimers, and that leads to a very trivial effect. You get isolated spin 3/2 moments that give you a Curie term, and that's an effect that dominates the thermodynamic susceptibility to measure it. So that's not a good probe of the physics of the spin liquid. But NMR is immune to that. NMR is sensitive only to what's happening here because the NMR nucleus is somewhere in the middle there. And so it's good to focus on what the NMR does. And the basic result over many, many years of experiments is that there's a very broad, very characteristic and broad line that develops at low temperature. With the broadening that's sort of Curie-like, it's 1 over temperature, increases with temperature dramatically, and has some characteristic dependence on the impurity density, on the density of excess gallium, which looks approximately linear, but that should be taken with a pinch of salt because it's a very small range of x over which it's fit. So if you think of these chromium spin 3/2 moments as just classical vectors that can point anywhere in spin space, the Hamiltonian is just a sum of squares. So the total spin on every tetrahedron must be 0, the total spin on every triangle must be 0 at 0 field. And the point Henle emphasized many years ago is that there's lots and lots of ways of making each of these brackets 0. And so there's a huge degeneracy of ground states where every simplex is quote-unquote satisfied. If you, on the other hand, now have non-magnetic impurities, the situation changes. If you just have one gallium anywhere, it doesn't do much because the best it could do is it could try and create a triangle where there are 2 spins, not 3, but 2 spins can still add up to 0. But if you have now pairs of gallium on the same triangle, that triangle finally has just 1 spin left, if you just think of that triangle, and there's no way it can add up to 0. It's just a single moment. And this rather elementary observation can be used to make the following point. If you now imagine you're at 0 temperature and you're averaging over all these ground states where the spins add up to 0 on every simplex, and then you turn on an infinitesimal magnetic field in the z direction, the total spin you get, the total polarization you get is half because you're going to double count every site, it's corner sharing. times the sum of the spins on each simplex. Now the spin on simplices is 0 except this defective one where it's just fully polarized. And the half then tells you that the saturation moment at 0 temperature is not S now, it's S over 2. So in this kind of very restricted sense, you can say that your spin 3/2 has got fractionalized into a half, right? This was the point he made many years ago. But it's not clear whether this argument goes through really at finite temperature when there are entropic effects, and this is not so simple. So what we had done some years ago is developed an effective field theory, which is basically a self-consistent Gaussian description for the underlying spin liquid, modified to take into account vacancy. The way we took vacancies into account is we just set the Gaussian field to 0 at the vacancy side, and the lone spin on a defective triangle you have to handle more carefully. So there we make no approximation, we retain it as a unit vector or a vector of fixed magnitude S. And so then you have a vector of fixed magnitude S interacting with this classical spin liquid background, which is approximated by a self-consistent Gaussian field. And you then ask what the physics is of the magnetic response of this system. And it turns out that you can actually do the full calculation and you can make the following simple observations in the low temperature limit. The lone spin behaves like it sees a field H over 2, not H, if you apply a field H. And then it creates the spin texture in the nearby spin liquid, which kills half the moment generated by the local spin. And so the net effect is exactly the susceptibility of a spin S over 2 at the classical. So this simple argument of Henley's that's only true at 0 temperature actually works, at least in this effective field theory, and makes a prediction. It predicts the shape of the texture around this spin cluster, this spin moment, and it also predicts this. And so you can then use this theory and our knowledge of what the gallium NMR nucleus is and what the hyperfine couplings are to actually model the line shape that's measured experimentally. And we did that. And we found pretty good agreement with the broad brush features of the answer. The only thing that we got wrong was when the experimental value of the doping was some number, we had to use a slightly different of doping. And that's probably because we assumed that the dopants go in stochastically in a completely random way, but it's not quite clear if that's correct, and maybe there's some clustering effect in these solid solutions. So now let me come to the more recent work with George, which is an extension of this idea to edge sharing motifs. So let me go a little bit slower now because this is relatively unfamiliar material. So we are imagining that you could have situations where the second neighbor and the third neighbor exchange on a honeycomb antiferromagnet is comparable to the nearest neighbor exchange. And we are starting to think about this situation from the idealized limit where they are large enough that the Hamiltonian is just sum over the hexagons, the total spin on each hexagon square. That's the edge sharing analog of what happens in SCGO. I should emphasize at this point, this is a purely theoretical investigation. There isn't a material that directly maps to this kind of a model, but there are several examples where second and third neighbor exchanges are 20% away from what you need to have the Hamiltonian like this. So let me sort of set up some notation. So first of all, that's the honeycomb lattice. And it's a bipartite lattice. So I have this two sublattice decomposition into little r A and little r B, two kinds of sites. This is the graphene lattice. This would be the two sublattices of the graphene lattice. And I've marked centers of the dual lattice, which is a triangular lattice, which is the lattice you get by connecting the perpendiculars that go through the edges of each of the graphene lattice links like this. You get a triangular lattice. And that triangular lattice has a 3 sublattice decomposition. So this is, for example, an A-type site of the triangular lattice. That's a B-type site, and that's a C-type site, right? So A-type site is surrounded by 6 sites, which are B, C, B, C, B, C, like that. Okay? So that's the basic structure. And now we want to play the same game and come up with a sort of a large N inspired effective field theory that describes this classical spin liquid on this lattice. And there's a kind of a more unfamiliar and perhaps more non-trivial way of thinking about it, which is that you try to decompose your, instead of going through the whole rigmarole of deriving a Largen expansion and asking what the saddle point is and so on, there's a nicer way to think which gets you the same answer more easily and more intuitively. You decompose the spins into what I call a dipolar part. This is the part that respects the fact that in the low temperature limit, all the spins on a hexagon would like to add up to 0. And a charge carrying part, which is the part that violates this energetic constraint in the low temperature limit. And the way you do that in this case is take a spin on the A sublattice of the honeycomb net, let's say this one. It's surrounded by 3 spins, 3 sides of the dual triangular lattice RA, RC, RB. And the decomposition then of this spin is into 2 terms. One is this, and they both of them sum over all the triangular lattice neighbors, these 3 sides, 1, 2, and 3. And these 3 sides host 2 different variables. One is what I call tau, the other I call zeta. And on the A sublattice, you have tau plus zeta summed over the 3 neighbors. On the B sublattice, you have tau minus zeta. So you've gone from a description in terms of vectors that live on the honeycomb lattice to 2 sets of vectors, tau and zeta, that live on the dual triangular lattice. Okay. And now the effective action that you get if you think in sort of a Largen way, which is what I did in my second lecture in school, for example, is very easy to write down. It decomposes into 2 terms. One that depends purely on zeta, one that depends purely on tau. The reason there's no coupling between them is that one of these is chosen to be purely dipolar and the other is chosen to be purely charge carrying, so they don't mix. The effective action has just these 2 terms, and it's only the action for the tau that knows anything about the energetic effects. This is the term that tells you that you like to, at the low temperature limit, have the net spin on a hexagon 0, and tau is the variable that violates that constraint. And the action for zeta, which is the dipolar part, is purely entropic. This is, roughly speaking, the weight of different ground state configurations of this classical magnet. So you have this effective action, and now you can play the same game. You can look at an orphan spin which is created when there's an anomalous clustering of vacancies, so that you have a hexagon now with only 1 spin left on it. And you have to be careful to model that lone spin on the hexagon by a unit vector, because it would be too crude to approximate that by a Gaussian. But the rest of the spin liquid you approximate in this manner, which is quite sort of accurate, it turns out, all the way to low temperature. And then you compute what you get, and you find that the impurity spin response in this case, which is the response of the diluted system with one of these orphan spins minus the background, which is the pure system, looks exactly like the susceptibility of a spin S over 3, not S over 2. So it's 1 spin has broken into 3 pieces in this more sort of complicated example. And you can check how well this prediction works. So here's some numerics that George did. The blue line is the prediction that it's the susceptibility of a classical spin S over 3. The red dashed line would be the susceptibility of a classical spin S. And the points are the numerical Monte Carlo data for this situation, and you can see it works exactly right. And so you now have examples where in this well-defined sense of Henle's, you not only have half-orphans, but 1/3 orphans. So that's the classical part of what I wanted to tell you. Now let me switch gears and talk about another problem we've been doing, this time with Sambuddha Sanyal. And that's to look at a tractable example of vacancies in a Majorana spin liquid. Majorana spin liquids, as we heard in some of the school lectures, are systems where the spins have sort of lost their identity as bosons and behave for all practical purposes as Majorana fermion excitations as far as calculating low temperature properties are concerned. What I'm going to show you is that there's some tractable models of these Majorana spin liquids that people have looked at in the past, which have which you can dilute. So imagine putting non-magnetic vacancies to these, and ask what the susceptibility is at low temperature. And you can show that the susceptibility becomes of this form. So let me say what these pieces are. There's one piece which is just a Curie tail. Just there's some constant which is depending on the impurity concentration times 1 over T. And then there is this anomalous behavior which is exactly like the physics of phosphorus doped silicon. This is the Bhatt-Lee kind of susceptibility. And this function n of gamma, which in the case of Bhatt and Lee was 1 over gamma square in 1D and something else in 3 dimensions that we've not been able to characterize precisely. In this case, you can characterize it precisely. It has this crossover. It goes from this 1D-like power law to something that's characteristic of a disordered fermion problem in 2 dimensions. This is called the Gade vector form. So this is sort of the punchline I want to get to in the next 9 minutes. So what I want to emphasize is that this then gives me an exact realization, an asymptotically exact realization, what looks like at least Bhatt-Lee physics in a 2-dimensional system of SU2 spins, which happen to be in a Majorana spin liquid state. And so following Bhatt and Lee, I can interpret C as the density of free moments, as the density of moments that never pair with anything else all the way down to 0 level. And n of gamma is then the density of singlet pairs with binding energy smaller than n. Okay. And so this raises an interesting question. Are some of these exactly soluble Majorana spin liquid models amenable to strong disorder renormalization proof approaches that will allow you to go beyond the tractable limit in the disordered case, in the strongly disordered case, and we don't have an answer for that yet. So let me tell you where these results are going to come from. They're going to come from the fact that these models are tractable, and I haven't written them down. I'll write them down in the next slide. They're tractable because they can be finally written down in terms of free fermions. They can be written down in terms of free Majorana fermions hopping on the honeycomb lattice. And the rule is that every time a vacancy enters the system, it binds a pi flux for these fermions to see. And that's the free fermion problem you have to look at and understand the properties of. And what's going to turn out is that this function n of gamma is going to be the integrated density of states for single particle states of this free fermion problem, excluding 0 modes. And this constant C, this Curie constant C, is going to be related to the density of exact 0 modes in this spectrum. And this crossover I talked about is an interesting crossover which is induced by vacancies in the chiral orthogonal universality class of Anderson. And so it applies as well to undoped graphene with vacancy disorder, and we've looked at that as well in parallel. So let me tell you what is the tractable model I use to derive these results. So the model I'm looking at is the honeycomb model of Yao and Lee that many people here will be familiar with. They worked on it. So this is a model of orbital degrees of freedom that remain dynamical at low energies. Those are the tau, and spin full moments, spin half moments that have full SU2 interface. So it's roughly speaking a Heisenberg exchange for the SU2 moments on the honeycomb lattice, modulated by the dynamics of these orbital degrees of freedom. And the orbital degrees of freedom, if you ignore these spin-full moments, have exactly the physics of the Kitai. So the original motivation of Yao and Lee was to look at a low-energy effective Hamiltonian for a decorated honeycomb lattice with multi-spin interactions, but for us it's just a tractable limit of a Majorana. And the reason it's tractable is you can use this representation of Majorana representation of spin variables that was popularized by Svellik and by Deeptiman Sen and Sriram Shastri, and rewrite the problem as, I'll go through this calculation. You can rewrite the problem as 3 copies of the same Hamiltonian, and these 3 copies correspond to the X, Y, and Z polarization of the spin. So it's a spin 1 Majorana. Hopping in the background of a static Z2 gauge field, and in the ground state sector this Z2 gauge field is just 1 everywhere. There are no vortices, and the interesting thing is that the physical susceptibility becomes the density, is related to the compressibility of these canonical fermions that you can make out of 2 of these Majoranas. So in the end you have regular canonical fermions hopping on the honeycomb lattice, and you want to calculate compressibility. And so the susceptibility, like I said, is related to the compressibility, where this is the total density of states, including zero modes and the rest of the spectrum. And there's some subtleties with projection that I'll not go through in the interest of time. Vacancies are modeled simply by removing the corresponding honeycomb lattice sites, and we are careful to impose some sort of global compensation. So there's an equal number of vacancies on A and B sublattices, otherwise you get some trivial effects that you don't want to look at. And we put in some short distance correlations in the impurity ensemble to prevent the system from disconnecting into small clusters, which would also be a sort of a trivial effect. And we know from previous work that every time you have a vacancy in this situation, it binds a Z2 flux. So you have to put in a flux string going out to the edge of the sample every time there's a vacancy. And so we use semi-open boundary conditions to do calculation. And here's what we see. The first statement we can make is that every sample we look at in the thermodynamic limit, large enough system, has at least one zero. This is the fraction of samples with at least one zero mode, and it goes to 1 in the large element, right? The second statement is that the density of these zero modes is non-zero in the thermodynamic limit, and that's what this Curie constant is. So you can see we have actually converged very nicely to the thermodynamic limit. The density of zero modes is non-zero. And we see this advertised crossover, this function n of gamma, which is the integrated density of non-zero energy states up to energy 10 to the minus gamma, looks like this one-dimensional Dyson form, which is a power law, and then crosses over to this Gade vector, which is faster. The blue line is the fit to the power law, and the red line is the fit to this Gade vector. And the power law has some characteristic number which we can compute and depends on the density of impurities. And so we've done it at several density of vacancies, and we get different numbers, so it's non-universal. And the other thing we note is that the crossover length scale very easily and readily tracks the length scale that's defined by the density of zero. So somehow this crossover is controlled by the density of zero mode, and the zero modes are really crucial to this physics. And so let me tell you where they come from. This in many ways is the nicest slide because it requires no calculation, you have to just look at it. So here I've drawn a picture of a cluster where there are 6 vacancies that come nearby. Okay? You can see that this 6 vacancy cluster has not decomposed the lattice into an inside and an outside, it's still fully connected, it's not broken it up into a cluster. Yet, because of the way they are arranged, it hosts an exact zero mode of this hopping problem with pi flux bound to every vacancy. Here's another more complicated version where there's a different cluster of 7 vacancies that also hosts a zero mode like this. This one is very special. If you have any bond modulation, any hopping disorder, any disorder at all in the hopping amplitudes, this mode will just go away. You can check that. But this mode is completely robust to all forms of bond disorder that involve hopping between opposite sublattices. The only thing that kills it is hopping within the same sublattice. And so these zero modes are really a robust feature both of the graphene problem and this Gittire model, because the difference between them is just this pi flux bound to every vacancy, and that's a kind of, if you wish, that's a form of bond disorder. So this is a very robust property of both lattices. And the key point is that because they're completely robust to disorder, there is some hope that this physics will survive beyond exact solutions and mean field theory. Because if you think about how you might go beyond mean field theory, you will introduce some interactions between these electrons. And if you do some sort of a Hartree theory for these interactions, the first term you will get is something that modulates the hopping on bonds near the vacancy. And if you have any physics that depends very specially on all amplitudes being exactly equal, that will not survive. But here this is completely robust to disorder, so there's some hope that it survives. And actually we are going to look at some interacting versions of the graphene tight binding model to see if this is really true. So with that, I have 1 minute left, so let me just not talk about competing work and just put up the slide of collaborators. Thank you.